So what is a dilution? When I talked about terminology at the beginning in the first module, we talked about concentrated versus dilute and how these are relative concepts. Dilute just means I have less particles of something dissolved in the solution as compared to another solution. So the easiest way to think about it is like, say you take a package of Kool-Aid and you dissolve it in water, you add your sugar to it, but you decide that it has too much sugar. You may take some of that Kool-Aid and pour a little bit of it in a glass and then fill the rest of the glass with water to dilute it. It's got less color now and less sugar now. That's diluted compared to the original starting container. Dilutions are always relative to another container, another thing that you have. It's not just that a solution is concentrated or dilute per se, it's always in comparison to something. So concentrated solution, we add water to it, we form a dilute solution. The concentrated solution is called our stock solution or often our reagent or reagent bottle. So this stock solution is often what we buy from the store. Or sometimes we will be in a lab and we need to prep something for students. We'll take a solid and we'll make a solution out of it. We'll make a stock solution that has a higher concentration so that we can make less of it. We then tell the students to grab, say, 10 mils of it and dilute that 10 mils up to 50 mils or whatever they need to work with. It allows us to use less of it. It actually creates less air that way, less money, because we can buy it less often, less storage space, etc. So we often use stock solutions, and you're going to see this come up in lab in second semester. So the equation that we use here, I call it M1v1 equals M2v2. There are other forms of the equation we'll cover as well, just to show you guys what we mean by this. And I'll cover those in the very next slide. But I call it the M1v1 equation. So the moles of your solute in the concentrated solution equal the moles of solute in your dilute solution when the entire solution has been diluted. What do I mean by that and why do I specify? Let's say that you have a 50 ml solution. You take that entire solution and you dilute that up to a total volume with water to 250 mils. You have not changed the amount of solute in there. You have the exact same moles of solute that you started with. Now, let's say and that's what I mean by your entire solution is diluted. All 50 mils has been diluted. And in that case, the moles of your solute in the concentrated solution does equal the moles of solute in your dilute solution. But let's say that I gave you a 50 ml solution and you only took 25 mils of it. 25 mils of it was diluted up to 250 mils. Well, the moles of solute in the concentrated solution aren't technically equal to the moles of solute in the dilute solution anymore because I only took half of that concentrated solution. But they're still relative to one another because the solution you have is a homogeneous mixture. So if I take half of it, then I've taken about half the moles that were in the original solution. So it's still relative. Again, we are going to use this equation, M1v1 equals M2v2. I'm going to show you two other forms of it on the very next slide. But the concentration and volumes of your stock solution, meaning your more concentrated solution, and your dilute solution are inversely proportional. Remember, molarity times your volume gives you your moles. This we covered in the last video. So you don't have to use this equation. And you've got to be careful when it's appropriate to use this equation. It is only appropriate to use for dilutions, not any other cases. Students use this equation all the time when it's not appropriate, and you will not get credit for that. You can only use it if you're just diluting a solution, not mixing it with something else, just diluting. So the other equations you'll see is C1v1 equals C2v2. We've already said M1v1 equals M2v2. You'll see M conc V conc equals M dil V dil. This C meaning concentration, V meaning volume, M meaning molarity, V meaning volume, conc means concentrated, dil means diluted. But again, you can only use these equations when it's appropriate, so be careful of that, please. So let's work 2 examples here. You need 150 mils of a 0.50 molar HCl solution, and we have 12 molar. What do? Well, M1, V1, M2, V2. I recommend setting it up this way and writing down everything we know. M1 is your starting concentration. We have 12 molar. That is our stock solution. M1 will be your highest concentration. V1 is how much of V1 do I need to use to make my diluted solution? I don't know, that's what I'm trying to find out. M2 is the concentration we're trying to prepare. In this case, that would be 0.500 molar. V2, 150 milliliters. Now, the nice thing about the dilution equation, you don't have to convert this to liters. You're welcome to, but you don't have to because they're going to cancel out. So, go ahead and solve for what you want to find. We want to find how much of V1 do I need to make the solution. If I rearrange this equation to solve for V1, or actually I'm going to use this equation because I've written it with the form of M. Rearrange this equation to solve for V1. I get M2 times V2 over M1. Plug in what we know. We know M2 is 0.500 molar. V2 is 150 milliliters. M1 is 12 molar. So you see, the molars have canceled out here and I'm left with milliliters. You're welcome to convert that to liters. Doesn't matter. Because we're probably not going to measure things in liters anyway. But if you had to cancel out milliliters, if we're looking for concentration, those would cancel out as well. And you can see that in the examples at the end of the chapter. Our answer here is 6.25 milliliters. So what does this mean? What do I do with this information? Well, this means that I'm starting off with a flask that's 12 molar HCl. I want a 0.5 molar solution of HCl. So I'm going to transfer 6.25 milliliters of that 12 molar solution into a new volumetric flask. Truthfully, I'm going to add some water to it and then add acid to it and then fill it up to the top, but we'll get to that when you get to lab. And I'm going to make a total of 150 ml solution. So if I had to describe in words what I would do, I would fill a 150 ml flask with about 100 mils of water. I would pipette up 6.25 milliliters of the 12 molar HCl, stock solution, add it into the water. I would then carefully dilute the total volume until the total solution until the volume was 150 mils. Why am I being so specific in the way I say that? Well, acids react with a lot of heat with water. So if I add a little bit of HCl to a lot of water, that water is able to dissipate the heat that's being generated from that acid being dissolved in the water. If I do it the other way, and I have, even though it's only 6.5 mils, if I have 6.5 mils of water or acid in there and I start adding water to it, it's going to get really hot and it doesn't have anywhere to dissipate the heat, because it's just adding to more acid. So Whenever we add acid to water, we always do it in that order. We add acid to water, never water to acid. Now, I cannot put 150 mils in here. I can't even put 143.75 mils and then add the acid in there. It's not guaranteed to be 150 mils. Some compounds you're going to find out fit better together than they do by themselves, so there'll be less volume. Some take up more space because they need to maximize for intermolecular forces. We're going to learn about those in another chapter. So what you'd always do is if you need 150 mils, you're going to put about 100 mils of water in there, add your acid to it, and then once dissolved, once that's in there, just kind of swirl it around, make sure it's diluted, you're then going to add water to it. That point, that acid is very low concentration, and it won't be that dangerous to raise the volume from there. But you do want to be careful to always add acid to water. This is how you would go about doing that, doing it in the actual lab, and here is how much of that solution I would actually need. Let's work one more example for this section. A 5 molar NaCl stock solution is available. How would you prepare 300 mils of a 0.1 molar sodium chloride solution? So this is definitely dilution. M1v1 equals M2v2. So write down what we want to know. Well, we've got 5 molar stock solution. So that means the M1 is 5 molar. We want to prepare 300 mils, which means V2 is 300 mils. And note the decimal place there on the number. That's keeping my precision in my measurement, so I cannot drop that. That's telling me I have 3 sig figs. And I want it to be 0.1 molar. So I am looking for V1. There are examples at the end of this PowerPoint looking at things other than V1. There are in your homework, your textbook, etc. So please work other examples as well. Solving for V1, M2 is 0.100 molar. V2, which is what I was just trying to write, is 300 milliliters. M1 is 5 molar. So V1 is found to be 6 milliliters. So what do? I'm going to dilute 6 milliliters of the 5 molar stock solution to 300 milliliters total with water. Now, acids, I got to be careful the order I do them. Salt solutions, they don't care. You can add the salt in the bottom of the flask and add the water to it. It won't matter. But make sure you realize that this equation is only appropriate if you are just diluting. You're taking some of your solution and you're diluting it with the same solvent. This is not appropriate for mixtures.